Hello and welcome to 15th lecture in 19th chapter in our comprehensive course on AI, ML and DS. Now here we were discussing these various distributions, statistical distributions, and we used this website also where you can actually simulate each of these distribution. So now let us continue further. Last was this T distribution. Now we want to discuss some of this distribution with a different approach. The different approach means now this time we will try to actually create data using which follows that distribution, so, using code. The purpose is to introduce you certain functions in NumPy, Pandas, or other Python libraries by which you can create data of required distribution. So we will talk this distribution: normal distribution, binomial, Poisson, exponential, and logarithmic. So among all these we have already discussed, but among all of them, these five are perhaps the most important from data point of view. What is normal distribution? Then it is symmetric bell-shaped curve which is characterized by a mean and a standard deviation, and values tend to cluster around the mean. That popcorn example or that sand passing through thrown on a sieve, that example. Okay, so here that is one example. Adult human height, shoe size of males, that is always following normal distribution. This was an actual experiment done by a professor in one British university, and this is the sample of around maybe I think 60 or so students, and it was found that these students are the tallest, so they were kept at the middle, and all that behind them they were also tallest, so they were kept at the middle, so as to create an idea like that curve. Okay, and these students are the minimum in height, so they were kept on the sides, and you can see that the height distribution follows normal curve. Okay, bell curve. So adult height, then application is understanding of that distribution of height can help in clothing design and clothing design, shoe design. So I already discussed that. Public infrastructure planning, so that if you are designing say public toilets or public urinals, so at that time you have to think that they should be able to accommodate maybe around this. Okay, so these are the average actually. These are not tallest. I say tallest. That was my mistake. Sorry. Average height, and that is the maximum number of people have average height. These are some tallest people, extreme height on one side, and these are some shortest people, extreme on the lower side. They are on one side, but majority of the people they have this height, right? So as a result, the public infrastructure should be able to satisfy these people. Say that will be around 85% or 95% of the people. Okay. Then binomial distribution, that is used for quality control in the manufacturing. Now that we have done all that, so that is why I am not discussing this, because how defective products can be detected we have done discussion. But let us create a hypothetical data. Okay, so suppose total number of items which are produced, which are called trials, is n. Probability of suppose an item which is being defective, which I call successful event here, that I can that means defect occurs, that is a success in this case. So that is suppose p, and the number of items in a batch follows binomial distribution. That is what we are assuming, and we will create the data itself that will follow binomial distribution. How to create? So import numpy as np, take n is equal to some number, so number of trials, so that is total number of items which are produced. Okay, take some probability of success is 5%, that is probability of finding a defective item, that is 5%. Then generate data, so np.random.seed, that is just for reproducibility. Even if you don't keep this, then also the data would be generated following binomial distribution, but with each next iteration, that means when I execute this same code again after kernel restarting and so on, then it might be that it will generate different data. All will be following binomial distribution, but the data points will be different. Okay, so this seed keeps the same data would be generated on every execution of this code. Now np.random.binomial, this is what I wanted to introduce. That is why we are doing this repetitive discussion. So that is a function in NumPy library, just like we earlier used np.random.randint for creating random integer, np.random.normal for creating normal distribution. Similarly, np.random.binomial. Okay, and if you forget, then I have already shown you the trick that once you have imported this, then you write np.random dot and press the tab character. Then all available choices, binomial, random, randint, all will be displayed to you. So you will immediately choose the binomial, right? N and p you have to specify. Okay, and size you can specify how many such batches of 100 trials. So now you can understand that quality control is not so easy thing. Okay, you are controlling creating 1000 batches, each having 100 items per batch. So that is, if I gave earlier example of keyboard defect, so how many observations will be required? 100 keyboards will be taken in one batch, and total such 1000 batches of 100 keyboards will be required. Then we will plot the binomial distribution, right? So if you plot it, then you will get this kind of graph. And data, I'm writing data, but entire data would be very big, but still let me plot that. Okay, so this is 4 defects, In first batch 9 defects, 6 batch like 6 defects in next third batch, and so on. So sometimes the defects are slightly more than 4, sometimes they are slightly less than 4, sometimes they are as large as 10 also, sometimes they are as small as 1 also. That is okay, but probability is 0.05. So if I just show only the top 5 observations, top 10 observations, then 4 defective pieces were found from first batch of 100 keyboards, 9 defective pieces, 6, 5, 3, 2, and so on. So this kind of probability distribution says that I am close to my desired quality control. Suppose quality control has given you this probability that probability of defective item should not be more than 5%, or that means the probability of defective item is 0.05%, 0.05, right? So you can see that here out of 100 keyboard batch, sometimes more than 5, sometimes less than 5, but it is not excessive, right? So that is fine. Now I can even visualize that to check that it gets the mean at 5, and uh, so that this probability is followed or not. Okay, so 0.05 means 5%, because when I convert into multiply by 100, then I will get it in 100%, right? So if I plot it now, how to plot? Let me, how to show this? Maybe I think I should plot this much on a separate graph paper, but then it will not show. Okay, everything should be in one cell only. Okay. And don't worry about the graph, code, because that is a quite difficult code. We don't plot probability mass function using matplotlib and scipy. We know now that Seaborn has can do the same thing in just 2 lines of code. Okay, by plotting a histogram and then showing that uh, KD is equal to true with Seaborn library. But here we are using matplotlib and scipy, so that is okay. But you can see this kind of data distribution is found. Now that is the characteristic and typical binomial distribution, right? So you can check earlier binomial we saw, yeah, this one. But here it was symmetrical. Maybe binomial. Here also it is symmetrical. So let me try to show you from here binomial. But let me change this P and like this. Okay, and this N. Okay, and I'm trying to make it similar to what we have observed. Okay, so you can see roughly it is now becoming similar. This tail is getting long. Sorry. The right side tail should be getting longer. Okay, that is my purpose. So you can see now that right side tail is getting longer. So that is this kind of distribution which we are seeing in this graph that we just now plotted. It is almost like normal distribution, but one side tail is longer. So there are certain values here, for example, where even more than 10 defects are also seen in the keyboards, but they are very rare. And always the characteristic of this distribution is found at mean. So on an average, the company has decided after doing this kind of experiment that on an average, of course, this kind of experiment means we have done this experiment using data, synthetic data, but the company will actually take 100 trials, and it will find how many 1,000 batches of 100 keyboards, and obviously it cannot examine all 1,000 batches, so it will examine some representative sample from that batches, maybe first batch, 11th batch, 17th batch, 23rd batch, and so on, and it will find the number of defective pieces, and it will get this kind of data which we created synthetically, and then plot the graph and find the mean. So that gives that on an average per 100 a batch of 100 keyboards, 5 keyboards are found to be defective. These are considered as extreme values, and they are outliers, and they are not important. Sometimes you got 10 or more than 10, maybe 15 or 12 keyboards defective, but that is okay. That is just a very small number. Probability is very less. And similarly, sometimes you got in entire batch of 100 keyboards, 0 keyboard defective. But again, that is just a very small or negligible probability. So what you have to see is where there is maximum probability. That is at 5. So you will say that at most 5 in one batch, that many keyboard will be defective. Now Poisson distribution. Now this is an interesting example of Poisson distribution. So calls at a call center. The number of calls received by a call center in 1 hour is a classic example. Another example is the number of visitors to a hotel. Okay, that is also an example of Poisson distribution. Now, first these calls to a call center. Suppose you are running a software company and you launch the new software, but you have to provide some technical support to your client. Now the question, you have set up a call center and you want to hire engineers, and you want to predict that how many engineers would be required in day shift and night shift also. But for that you have to first predict how many calls will come per hour in day shift and in night shift. So if only 2 calls are coming per hour, then just 1 engineer is enough. But if 2,000 calls are coming per hour, so then in that case One is your software is very crappy, but that is another matter. But that means that you have to provide more engineers to handle 2000 calls per hour, right? One engineer would not be enough. So you will not be unnecessarily hiring engineers and spending on salary if you can estimate how many calls will come. And surprisingly, how many calls will come at the tech support, that depends upon, that always varies according to Poisson distribution, irrespective of the business. Okay. So then, for example, here Poisson distribution, if I show this, okay, so how many calls will come, and lambda is a variable in Poisson distribution. It looks almost like normal distribution, but again, as I go on this side, you can see the tail is getting longer and longer. This curve on the right side will show you how the tail is varying. Otherwise, it is just a histogram only, okay, like this. So this is the Poisson distribution. So I can estimate the number of calls, prospective calls, and accordingly I can hire employees so that my salary bill is not excessive, and at the same time my customers do not have to wait for a very, very long time, right? So that is one example. And suppose average number of calls received by call center per hour is 50. Now, actually, these numbers were 18 in 1 hour, 10 in another hour, 16 in another hour, okay, 19 in another hour, and like that. So their average is 50. Now let us generate a code like that. So you are taking lambda is equal to 15, which is nothing but average number of calls per hour, right? So here that lambda, as you made smaller, the distribution became less because say lambda 1, then you got this kind of distribution. But as lambda increases, number of calls per hour 40, then it approaches almost bell curve, right? So that is the situation. Now lambda is 15, and np.random.seed, again, that purpose I have shown you just for getting same results every time. So np.random.poison. So again, you can see here it was np.random.binomial, right? Where is that? Earlier we produced that kind of, yeah, here np.random.binomial. Similarly, here it is np.random.poison. So NumPy library is very dynamic. It can generate all data distributions on its own. Okay, and let us show the outcome of generated data. So these are first 10 hours and the complaint calls received in that first 10 hours. Average is 15. So sometimes more than 15, sometimes less than 15, like that. Now let us visualize this distribution. Again, the code for visualization is not important because you see that there are ready-made such tools available. And in many of the tools like SPSS, SAS, etc., which are not much coding based, they also have user interface in which you just have to slide the lambda and slide for adjusting value of lambda, and it will plot the Poisson distribution. But you can see this is a Poisson distribution for lambda is equal to 50. It does not much look different, except that on this side, right side, slightly it is having a longer tail, right? So, and higher probability also. Okay, but important thing is where is the mean, where is the largest number of count or highest probability. So highest probability is seen in somewhere 14 region or 15, 16 region. Okay, so you can say that on an average 14, 15, 16, that will be the range in which the calls will be received, right? So let us see here. I adjust lambda is equal to 15, and I should get that kind of graph, right? So 15 exact, or I think I should be able to put, yeah. Okay, so this is the graph, and it is exactly this graph which we have plotted here. Okay, now exponential distribution. A very famous example was time between failure in the mechanical system. Now this is also important. There is some branch of data science called predictive manufacturing. Now what happens is there are certain machine parts which are very, very costly and which are made in one piece by order only by the manufacturing company. Now suppose you are running a firm, a dyeing house or a textile factory in which your machinery, each machine has only one or two such parts which are very costly and which are built by order only by the manufacturer of that machine which you are using in your textile factory. By order only means what? That those parts, if they fail, break, then you have to tell the manufacturer maybe 6 months in advance. So the question is, suppose the part has failed today. So will you stop? And that is a critical part without which your machine cannot run. So now in that case, will you stop your entire production because of just one machine part? And they are very costly, so you cannot afford to keep duplicate parts also. That means extra pair or extra part also. So what is the other better way out? Then the better way out is, can you predict when your machine part is going to fail? So yes, it is possible to predict time between failures in the mechanical system. That if first failure occurred at this interval, at this time, note down the date and time, next failure occurred at this date and time. If you have some past data, maybe just 20 observations, then you can easily predict that the next failure will occur in the month of October in 2025. So you can suppose that manufacturing company is taking 3 months to manufacture the part on order. Then you can order the, you know that now that machine part is likely to fail in October 2025. So you can order that in maybe February 2025 or March 2025 only. so that that company gets its 3 months time. Because if you urgently order when in October it fails and then you order, that company will charge you money for the urgency. But if you say put order in normal course and tell that company that okay, you supply it within 3 months, I don't have an issue, so then in that case you will get that competitive price, right? So that is called predictive manufacturing. Manufacturing industries often use these kind of machine parts. Not only manufacturing industries, the automobile industry also. There are certain cars like Rolls-Royce and Lamborghini and maybe some other, I don't know much about costly cars, but there are some other maybe brands which are extremely costly. And more important than costly is that those companies have the copyright, patent, so only they can produce the part. So even if you are willing to spend money, you cannot buy that part for that car from outside market. Okay, so then it is better to be able to predict. And these companies only nowadays have started putting sensors in your car, and those sensors are connected with the server of the company. So the company itself will tell you that's where your this machine part is likely to fail within 6 months. So please get it replaced within coming 2 months, and we will not charge any extra amount for that if you replace it within next 2 months. But if you come when it fails, then one, you will have to suffer the hardship, and second, at that time you will have to pay the charges for urgent delivery, right? So this is one case. Now let us try to, so that type of distribution, that type of case follows exponential distribution. Now here, let us say that we create one data set in which lambda is 21. Now what is lambda? Lambda is reciprocal of mean time between failure, MTBF. Okay, so mean time between failure is 2 hours, then lambda would be 1 upon 2 hours, like that. Okay, so that, I think here this 21 is written, that is wrong. That is reciprocal of mean time between failures. So it will be 1 upon 2 hour inverse, like that. Okay, 1 divided by 2 hour inverse. That would be the value of lambda. Hour inverse means hour to the power minus 1, right? Okay, so then let us assume that MTBF is 2 hours. Mean time between failure is 2 hours. So then lambda is 1 by 2, that is 0.5 hour. Then the time between first 10 failure is given by this data in hour. So first 10 this failure has already occurred, suppose, then you are asked to predict when will the next failure occur. Okay, so this is the time at which first failure occurred, the next time at which failure occurred. You may know that time can be converted into one universal timestamp using certain by programming techniques. Okay, so you may not need to provide time in the form of date, month, year, hour, minute, second. It will be that format only, but it will be internally converted by into one universal timestamp. Okay, so suppose these are those timestamps, and you are creating time between failures by np.random.exponential, and here you have to specify. Now you see that if you want to generate binomial, then np.random.binomial. If you want to generate that Poisson, then np.random.Poisson. Similarly, if you want to generate exponential, then np.random.exponential, right? So np.random.exponential, and you specify 1 by lambda, not lambda, but 1 by lambda. So your lambda is 0.5, or that means 1 by lambda is 1 by 2. So 1 by lambda MTBS, mean time between failure, that is 2 hours, and size is 1000. So you are generating the data for 1000 failures, and then print some first 10 values of data. So you are getting that these are the times between first 10 failures. Okay, now if you visualize this distribution and plot the graph, you can see a clear exponential distribution, right? So it is a very clear exponential distribution, and that means what? That between first and second failure, that is 0th and first failure, the time interval is largest. So that probability density is more. Okay, then the probability of having next each subsequent failure, that goes on decreasing, or the time between failure, that goes on increasing with each because on this axis you have plot time between failure, or in other words, time between failure is 1 hour, that has maximum probability. For this, time between failure has 2 hours, that has second highest probability, and so on. Or you can say that 2 hours, for that most of the area of the graph is confined in this 0 to 2 hours period. So you can say that the time the MTBF is most likely to be 2 hours for these machine parts. Now 2 hours is just an example, but it can be 2 years. Okay, so let us create this exponential here and satisfy ourselves that our code gave correct exponential. Now where is that? Yeah, this one. Okay, then you can see it is this kind of graph, and if I change beta here, beta is I think that lambda perhaps. Okay, so if I change it, you can get this kind of graph. So exactly same kind of graph is seen, right? Similarly, logarithmic distribution. Now this is also very common practical application of data. Frequency of words in a language, and this is used for detecting spam emails or etc. Okay, so in linguistics, the frequency of words in human language tend to follow a logarithmic distribution. This is also called Zipf's law. Zipf's law says that the frequency of any word is inversely proportional to the rank in the frequency table. Now that means we find that English or any language is very large, but you will be surprised that for computation, for high power computations of today, the corpus of the words which are used in day-to-day English, that is considered to be a very manageable, small corpus. Around some, as far as I have read the number, I'm not sure, but around 26,000 words or so. That is enough to make a data set of all the words which are used by day-to-day in day-to-day life by common people. Okay, so then you can even arrange that words according to their frequency. So that means, for example, words like th, the, then yes, no, they might appear very high in the frequency table, while certain words which are very esoteric, they may appear only less 3-4 occurrence in a corpus of so many words. You will find that if you make a corpus of 1 lakh words in or 10 lakh words, because 26,000 are the unique words, but if you want to include repeating words to find how many times each word is repeated, then you are taking 10 lakh words a corpus and arrange frequency wise them. Then th, the, and e's and r, they will occur maximum number of times, but on the other hand, very difficult words, they will occur in very less frequently, right? So then this law says that the frequency of any word is inversely proportional to the rank. So if there is one word whose rank is 2 and another word whose rank is 4, so that means rank is made 2 times more, okay, or that is rank is actually two times below, so reduced, because 2 is considered higher rank. So 2 will be most frequent. Then the word which is located at the 4th in the frequency table, that will have half the number of occurrences compared to the word which is located at 2 in the frequency table, right? So that is called Zipf's law. Now that is used, that law, that means if you plot the frequency of words, then that follows logarithmic distribution. Now this is used to find in text analytics and NLP, natural language processing, and they help algorithm prioritize more common words while still recognizing importance of less frequent words. So our chatbots, etc., ChatGPT and any other NLP based chatbot, they use this law and this logarithmic distribution. Okay, and as I said in email also, so if a word, if it contains some word like, say, you have won a lottery. Now lottery is not a very frequent word in a corpus of 10 lakh word, because how many people win lottery in the world? Okay, but if the email contains lottery, jackpot, that kind of word 20 times in one email, then it is flagged as a spam, because it is likely that it is some kind of scam, and the person is persuaded to share his bank account details and something, and his bank account details will be then used for some cyber crime, right? So this is one thing. Now here is the Python code to generate this logarithmic function. First, these are a is 1.07, that is called Zipf's parameter, distribution parameter, and size of the words to simulate is 1000. Again, I am using zips.rbs. This is important. You can see that any distribution, such a rare distribution, that is also available in Python. Of course, this time NumPy cannot give it, but you can have other library, scipy.states, and it imports this zips. Okay, I don't know how it is pronounced. Maybe I think F is silent, so zip, but import that library and then use this zip.rbs with some value of that parameter and some value of the size parameter. Okay, and what is to be provided, how to find that I have already taught you many times, so I will not go into that, but you know that, write zip f dot and put a question mark, or zip.rbs and then put a question mark, and you will get the entire function signatures. So what arguments you have to provide, what is their data type, integer or what, some examples also will be given in the documentation of that function, right? So we have found some word frequency. So this seems to be some word which is having very high frequency. Maybe it is like that e's and r. This is also reasonably high frequency. This is also reasonably high frequency. While these seem to be some words which are extremely rare in usage in the common man's language, like 1 times, 17 times, 11 times, like that. Now let us plot this frequency graphically. Then if you think imaginarily, then the graph would be following logarithmic function. Okay, so it is a log plot of word frequency. Now here let us try to find that logarithmic distribution. So log normal is there, but this was which kind of exactly logarithmic? Maybe I think log normal would be perhaps closer to that, right? So you can see this is the graph, and in my Jupyter notebook also, if I pass that a curve through these points, then I will get roughly that kind of graph like this. I have to pass a curve from the peak of each horizontal bar. Okay, it is not perfect, but that is because my sample is also very small, that is why. Okay, and in next, I think here this chapter will end. In next, no, we still have this inferential statistic, right? So then let us do this. Here we create a sample data for each distribution and visualize them in one go. That is just in case, suppose this probability playground is not there, or suppose someone is curious that how this person, Professor Adam Adam Cunningham of University of Buffalo. He has the copyright on this website, and how this fellow managed to make such an excellent website, because this automatic simulation and all that, so obviously there must be some code for that, right? So then he must have done somewhat similar to this is of course much simple, but we are plotting all the distribution. So this is trying to an effort to put all at one place, so that when you are revising, you don't have to revise this whole each distribution separately. You just revise this last example, so this one, and you have normal distribution, binomial distribution, Poisson distribution, exponential distribution, and log series. Okay, so then you can plot, and again, code that is not important, but you can see that normal distribution is here, binomial is here. This is log Poisson distribution, and you should immediately recall the example. Normal distribution, that popcorn or the sand thrown from other side of that sieve, or height of human adults, or shoe size of male, or then IQ of people, like that. Binomial, you should understand that this each is called one Bernoulli trial, and an experiment of maybe thousands of Bernoulli trials. Y is the count of the means how many times each experiment is run, and here on x-axis, in each experiment, how many times the coin was tossed. So this 10 is still small, but here it can nicely simulate binomial. So 10 times, and you perform your experiment of 10 coin tosses, that is one experiment, and perform it 250 times, right? Now then, this is Poisson distribution. The application I have already told you that it is used to model the duration between the calls which will come to call center, or the duration between the customer walking into a departmental store, or the duration between a customer walking into a hotel, that follows this Poisson distribution. So that helps you to decide how many employees you will hire in your departmental store at various different hours, and how many waiters you will hire maybe during the weekend, or during the other days of the week, and during the lunch time, and during the dinner time. If you have some idea like this, then you can hire optimal number of waiters, so that your customers get the best service, and at the same time you don't get the heavy wage bill. Okay, exponential distribution, that example of predictive manufacturing, that is the time between successive failures of a rare or costly machine parts. Logarithmic distribution, that example of the word frequencies, this. Okay, so how many times word is used in what is the count that a certain word is used. Then a few words are used very large number of times. For example, here we got that some words are used they are like A, N, D, THE, or maybe is or are like that. Okay, so these type of words are used large number of times. Some are used moderate number of times, or that means they are maybe like this kind of words, and some are used extremely rarely, like this. So that kind of behavior is logarithmic reduction, right? Okay, now what are the applications in data science? We have already done for each distribution, so I'm not discussing that. So in next lecture, we will be able to start basic inferential statistics. Those who think that those who have short memory, for them, we started the chapter here. Name of the chapter was Introduction to Basic Statistics, and we first did descriptive statistics, summary measure, 5-point summary, mean, median, mode, variance, and standard deviation, and that is measures of central tendency, and the measures of dispersion. Then understanding various distribution, that part we have done, but this part is still left, basic inferential statistics, that is introduction to hypothesis testing and p-values. So that we will do in subsequent lectures, and once that part is finished, then the chapter will be finished. So you can see that this chapter is becoming very long, but it is required. I think 14 lectures are already done. Now this is 15th which is being recorded, and still I think 3 more perhaps will come, right? So I can't help it, I have to teach thoroughly. So this is what is this lecture. Thank you, and see you in inferential statistics.